Alright, so just as a reminder to all of us, this is a rate law problem. This is something that you will see on the exam. So let's go over this. We went over a similar problem on Friday. So first of all, when they ask for a rate law, we're looking for some sort of table. Second of all, we want to fill in this equation here. Okay, the equation we want to fill in is rate, which is how fast this reaction will proceed. And that's going to equal to your rate constant K times the concentration of your reactant. So we'll call this reactant 1. Okay, it's raised to some power. Okay, so we need to find K, we need to find the power A times the reactant I minus. Okay, that's raised to the power B. Okay, so we need to find A, we need to find B, we need to find K. Okay, so S2O8 is the reactants. So it's going to be the reactant raised to some exponent. The second reactant raised to some exponent. Okay, those concentrations are raised to the exponent. So if you're given this problem on the exam, let's say, what will you do? You'll be given the equation, you'll be given this table, and what we want to do is fill out K, the exponent A, the exponent B. So the first thing we want to do is compare some of these trials. Let's compare experiment 1 with experiment 2. Okay, you can do any order. I'll just do 1 and 2. Okay, we'll compare 1 and 2. So we have rate for experiment 1 divided by rate for experiment 2. Okay, that's going to equal to K times S2O8 minus 2 raised to the power of A times I minus raised to the power of B divided by K S2O8. This is for experiment 2. Times I minus raised to the power of B. Okay, so we got these reactants. Okay, and we got these rates. We got these concentrations. We need to figure out the exponents. So what's rate 1 for experiment 1? It's 2.2 times 10 to the minus 4. Okay, molar over seconds. Okay, what's rate 2 for experiment 2? Okay, 1.1 times 10 to the minus 4 molar over seconds. Okay, so what's K? Okay, S2O8, that's something we need to find. What's S2O8 minus 2 for experiment 1? Everyone agrees it's 0.08. Okay, raised to the power of its order of decay. Okay, raised to the power of its exponent times I minus. What's I minus for experiment 1? 0.034. That's raised to exponent B, bless you. And then let's do that over 2. Okay, what's the concentration of S2O8 for experiment 2? 0.08 MA. And what about I minus? 0.017 M. Okay. Is everyone okay with this? Can we simplify this? Okay, so the 0.080 to the power of A is going to cancel out with the 0.080 to the power of A. Everyone see that? Okay, this k is going to cancel. We'll get to that later. Okay, 0.034 divided by 0.017. So 0.034 to the power of b divided by 0.017 to the power of b is just the same thing as 0.034 divided by 0.017. I should also tell you guys the m's and m's cancel. Okay, I'm just moving the individual b's to the whole exponent. And this is, we'll just do that the same. This unit will cancel out with that unit. Okay, so 2.2 times 10 to the minus 4 divided by 1.1 times 10 to the minus 4. Okay, this is 2. Okay, if you do that on your calculator, you'll get 2. What is 0.034 divided by 0.017? Okay, if you do that on your calculator, you'll also get 2 and to the power of b. Okay, 2 to the power of b. Okay, so 2 is equal to 2 to the power of b. So what is b? Is b 0? Okay, 2 to the power of 0 is 1. Is b 2? 2 to the power of 2 is 4. Is b 1? 2 to the power, yes, 2 to the power of 1 is 2. So b is equal to 1. Okay, so this means this reactant I minus decays with first order kinetics. Okay, first order kinetics. It's decay. We find out how fast the reaction is, how fast the reactants decay. We find out how fast this reaction is, how fast the reactants decay. So this particular reactant is going to decay with first order kinetics, okay, which means these equations. Okay, which means these are the equations for first order. Okay, so we'll talk about this later. Right, let's figure out A. Okay, so which experiments do you want to compare? I think I want to compare. We compared 1 and 2. Okay, what should we compare now to find the exponents here? We found b is equal to 1, so I think I'm going to compare 2 and 3. Okay, does this make sense? Okay, I see some nods, good. So we will compare 2 and 3 then. Okay, so let's compare experiment 2 with experiment 3. Experiment 2 over experiment 3. Alright, so this will be rate 2 over rate 3. Okay, is equal to K times the reactant S2O8 minus 2. Okay, raised to its order of decay times I minus raised to the power of B, which we solve for 1. That's its order of decay. Right, so rate 2 for experiment 2, let's substitute our values in. Rate 2 for experiment 2 is 1.1 times 10 to the minus 4. Okay, equals K. Oh, sorry. Let's do this way. Okay, rate 2 is 1.1 times 10 to the minus 4. Okay, S2O8 minus 2 is 0.08. I'm just substituting values here, so I'll just go ahead and substitute values from the data table. 2, and 3. Okay, I minus for experiment 2 is 0.017. Okay, raised to the power of b, which we found out was 1. And then rate 3. What is rate 3? Let's look at our table. What do you guys see? Okay, 2.2 times 10 to the minus 4. Okay, K we'll find out later. S208, this S208 minus 2. For rate 3, experiment 3, I'm getting 0.160. I minus for rate 3, experiment 3 is 0.017 to the power of b. Okay, we already know b is 1, so that's okay. All right, what can we cancel? We'll find these k's later, the rate constant k's later. Okay, 0.017 m to the power of b in the numerator cancels out 0.017 m to the power of b in the denominator. And then what's 0.08 divided by 0.160? I'm going to move it out a little bit. Okay, I can push those exponents out. This and this cancels. What's 1.1 times 10 to the minus 4 divided by 2.2 times 10 to the minus 4? Alright, this 1.1 times 10 to the minus 4 divided by 2.2 times 10 to the minus 4 is 1/2. Okay, what's 0.08 divided by 0.16? 1/2 to the power of a. So 1/2 to the power of a is equal to 1/2. So what will a be? Would it be 0? 1/2 to the power of 0 is 1. Anything to the power of 0 is 1. 1/2 to the power of 2 is 1/4. 1/2 to the power of 1 is 1/2. So what will a equal? 1. Okay, so just like I minus, in this problem, S208 minus 2 will decay with first order kinetics. Just like I minus. So now let's write our equation. We're not done yet. Almost done. We're not done yet. So this is not our answer, by the way. Rate is equal to k. Let's substitute in a for 1, b for 1 in our equation. Okay, a is 1 and I minus is 1. Okay. So we found a is equal to 1, b is equal to 1. The overall order is 1 plus 1. If this reactant decays with first order and this reactant decays with first order, the overall order is 1 plus 1, and that is 2. Now we have to find k. So a lot of students in the past, past 8, 9 years I've been at this school, they'll just leave it like this and then, think it's done. Okay. Now we have to find k with the right units. Okay, find k, which is the rate constant. Okay, with the right units. Alright, so pick anything here. Can you pick one, Leslie? 1, 2, or 3? 2? Okay, so what is, we will pick experiment 2. You can pick 1 or 3. I thought you said 2. Okay, experiment 3. Okay, so what is the... Huh? You can pick 2, we can pick 3. We can do 1, 2, and 3, it's fine. Okay, give me rate for experiment 3. Okay, and the units are molar over seconds. Okay, so units are important here. Okay, this is K. This is what we're trying to solve for. What is S208 minus 2 for experiment 3, Leslie?
0.160.
Big M raised to the power of what number? Raised to the power of 1. And then times, what's I minus?
0.07.
Raised to the power of what number? That's also raised to the power of 1. Good. All right, so let's do our math here. So I'm going to take the point once. Oh, by the way, this is M. Okay? M. Okay, right? So this brackets means M. Okay, which is moles over liter, which was one of the test questions, okay, in our last exam. All right, so what's 0.16 divided by 0.017? And that is M squared. 0.16 times 0.017. M times M is M squared. Okay, are you guys getting 0.00272? Okay. K 0.00272 M squared. Okay, M squared, because M times M is M squared. Okay, it's equals to 2.2 times 10 to the minus 4 molar over seconds. Okay, so K, isolating K, we get 2.2 times 10 to the minus 4 M divided by 0.00272 M squared. Okay, M squared, molar over seconds, molarity over seconds, M squared. Okay, everyone see this with me here for a second here? The units. Okay, one of these M's, do you guys see this? One of these M's will cancel out with one of these M's. Okay, what am I left with in the denominator? M. And what else? Times seconds. So what's 2.2 times 10 to the minus 4 divided by 0.00272? What do we see? .081. Okay, M is in the denominator. Is that correct? Yes, and seconds is in the denominator. Is that correct? Yes. So this is K. This is K. Okay, so our final answer. This is what we want to report on the exam. Okay, is rate is equal to K, which is 0.081. Okay, molar times seconds in the denominator times concentration of S208 raised to the 1 power times the concentration of I minus raised to the 1 power. Remember, this exponent we calculated as 1, and this exponent we calculated as 1. So this is our answer. So we have a way to check our answer. Okay, how can we check our answer? So how do you want to check it again? You pick any number, Leslie, experiment 1, 2, or 3. Okay, let's check our answer. We'll do experiment 2. Check our answer with experiment 2. Okay. So rate is what we'll solve for here. All right, we have 0.081 in the denominator, molar in the denominator seconds. What is S208 minus 2 for experiment 2, Leslie?
0.080.
M, okay, 4. Raised to the power of 1. And what about I minus? m raised to the
One.
1 power. Correct. All right, let's look at our units just for a second here. Okay, this m in the denominator will cancel one of the m's in the numerator. And so what do we get here? What's 0.081 times 0.080 times 0.017? This m cancels. We're left with molar over seconds. 0.081 times 0.080 times 0.017. What's that? 1.10 times 1, 2, 3, 4 times 10 to the minus 4. Right? Did you get that? And look, what do we have here? Experiment 2, which is what Leslie chose. And yep. Do you want to do experiment 1? Okay, what's 0.080 raised to the power of 1 times 0.034 raised to the power of 1 times our rate constant 0.081. Okay, if you do that, you will get, what will you get? You will get 2.2 times 10 to the minus 4. Okay. If you do 0.160 times 0.017 times 0.081. I did it on my calculator before class. Plug that in. 0.081 times this. This gets raised to the 1. This gets raised to the 1. You're going to get 2.2 times 10 to the minus 4. Okay. So you can plug in experiment 1 values, experiment 2 values, experiment 3 values. So this is a way just to check your answer. All right, so we will stop there. We'll review this again when the test comes, but this is called a rate law. Okay, you want to compare your experiments. Okay, your final form should be something like this. Okay, final form should be something like this. Okay, put the right units on K. Concentration raised to the correct power. Okay, the overall order of this is 2. Okay, this decays with first order, and that decays with first order. The overall order of this reaction is 2. Okay. Oh, one more thing I want to tell you guys. Sometimes some textbooks will call this, you see this? Okay. We can also write it in another way. We can write this another way as rate equals 0.081 m to the minus 1 seconds to the minus 1 times S208 minus 2 times I minus. Okay. So you can also write it m to the minus 1 seconds to the minus 1. Okay, you remember, if you move it to the numerator, it's m minus 1. If you move it to the denominator, it's m. Seconds is in the denominator. If you want to move it to the numerator, it becomes, yes, seconds to the minus 1. Okay, so you may see this like this, or you may see it like this. Okay, both are correct. M to the power of minus 1 seconds to the power of minus 1. Okay, so I think your homework has some more practice, so go ahead and do that for your homework. And then we'll move on to some equations here. So we're on page 9 of our notes. All right, so you can bring this to the exam. Okay, so bring this equation sheet to the exam. It tells us, how we calculate decay. Okay, if the reactant decays with 0 order, first order, or second order. So bring this to the test. Okay. All right, let's say this is for the reaction A goes to B. Okay, A is the reactant and B is the product. Okay, bring this to the exam. Okay, let's say A, this reactant decays with zero order kinetics. Okay. So rate equals rate constant K times A to the power of its decay, and the order of decay, let's say it's zero order. Zero. Okay, anything to the power of 0 is what number? 1. So here rate is equal to K. Okay, that's what we see right here. Okay. Rate is equal to K. Rate is equal to K. Okay, so concentration over time, so rate is equal to K. Concentration over time looks like this. Okay, this is concentration on the y-axis, time is on the x-axis. So another thing, anytime you write a graph, make sure you label your axes. Okay, make sure your axes are labeled. Otherwise, the graph, doesn't have any meanings. So label your axis. And this is the rate law. Okay. How much A remains after initial amounts of A exist. Okay. So this A naught is the initial A. Okay, what is A then? Final. Okay, what is K? Okay, K is this rate constant that we found in our last problem for this reaction. And what is T here? It's not temperature. Okay, what are we measuring in decay? What is decay? Over what? Time. Okay, so this lowercase t is time. So if the reaction is decaying with zero order, okay, this is the equation you want to use. So make sure you bring this to the test. Okay, if that reactant is decaying with zero order. Right, so this is a straight line. The concentration over time is a straight line. Simple, zero order. And what happens if you take A, for this reaction A goes to B, and you double it? Okay, how fast will the reaction go if A decays with zero order? Okay, if you double reactant A, how fast will the reaction go? The same. If you triple A, how fast will the reaction go? Okay, the same. Okay, because the rate is just equal to how fast the reaction is proceeding is just based upon K. Okay, rate constant K. All right, and for zero order, this is the equation for the half-life. Okay, do we know what half-life is? Okay, half-life by definition is a time. Okay, so half-life is a time when 50% of the substance is gone. Okay, so it could be seconds, it could be hours, it could be days, it could be years. Okay, like the nuclear waste, uranium or polonium or plutonium, they have half-lives in the, thousands of years. Okay, so the radioactivity still will remain. So it's a time, first of all. Okay, seconds, minutes, hours, days, years. And it's a time when what is left over? What has decayed? Half. Okay. Time when 50% of the material has decayed. Okay, what equation will you use for the half-life if you know this reactant will decay with zero order kinetics? Okay, this is the equation. Okay, concentration of A divided by 2K. What does this A naught mean? Initial. Okay, starting. Okay, how much you start off with? How long will it take before 50% of your initial is gone? Okay, how much will it take before 50% of your initial is gone? Okay, so that's zero order. Let's say this A decays with first order kinetics. Okay, so we'll do that in blue here. No, We'll do that in green. Okay, this time A is going to decay first order. Okay. So A to the power of 1 is what? A. A to the power of 1 is A. Correct? So if A decays with first order, this is what the graph will look like, concentration over time. And this is really a hard graph to mathematically analyze. So what we do is we do a transformation. This is called a linear transform. Okay, are there anybody here who's a math major? Okay. So we do a linear transform, concentration over time. I had an advisee 2 years ago who I was advising. She was a chemistry major and a math major. So she was doing all these like such weird math. I could never believe looking at her math book. So we do what's called a linear transformation. Okay, linear transform. Okay, so how do we convert this curve, which is really messy to analyze, into a line, which is y equals mx plus b? Okay, what do we need to do? Okay, we take the natural log of the concentration. So in zero order, we just take the concentration of A and divide it by the time. Here, if A, or any reactant, is going to decay with first order, to get a straight line that's easy to mathematically analyze, we plot natural log of A over time. Okay, when we do that, we get a nice line. Okay, slope y equals mx plus b. Okay, m is the slope, b is the y-intercept. And the equations, this is what we're interested in finding. This is the equation for first order, okay, after you do the linear transform. Okay, natural log of A equals natural log of A naught. What is A naught again? Initial minus K. What is K? Okay, this time it's first order. And what is T? Time. So this is the equation you want to utilize. Again, bring this sheet to the test. So this is the equation you want to utilize. You want to use if it's zero order. Okay, this is the equation you want to utilize if it's first order. All right, what happens if you have a reaction that's A goes to B, and you know A decays with first order kinetics? Okay. What happens if you double A? Well, how fast will the reaction go? How fast will the reaction proceed? Okay. If you double A, how fast will the reaction go if it's first order? Okay, it will double. If you triple A, how much will the reaction go? Okay, if you quadruple A, how much will the reaction go? Quadruple. Okay, so if A decays with first order kinetics, you double it, it goes twice as fast. Triple the reactant, it goes 3 times as fast. Quadruple the reactant, it goes 4 times as fast. And this is the equation for the half-life, natural log of 2 over K. Okay, natural log of 2 over K. Right. By the way, I forgot to mention to you guys the units. Okay, K will have different units. This is what makes it difficult. The units for K, rate constant, is molar over seconds. The units for K first order is 1 over seconds. Okay, if that reactant is going to decay with first order kinetics. So utilize this equation for the half-life, which is the time when 50% of the material is gone. Right, finally, we have second order kinetics. What is this about? Okay, let's say the reaction is A goes to B, and it's going to decay with second order kinetics. Okay, what will A be? Okay, the exponent for A will be 2. Okay, so now the rate will be, how fast it will be K times the concentration of A squared. Right? we'll do our concentration over time. Again, that is kind of hard to mathematically analyze, so we'll do what's called a reciprocal transformation. How do we get this to a line? Okay, we get this to the line not by plotting A over T, not by plotting natural log over time T, but 1 over the concentration. Okay, plotting 1 over the concentration divided by T, we will get a straight line whose formula is y equals mx plus b. M is the slope. Okay, this is a reciprocal transform. These are the equations we're concerning ourselves with if it's related by second order. Okay. So what is 1 over A naught? What is A naught again? Initial. Okay, what's K? What's T? Time. Okay. And when will you use this equation? When your reactant decays by how much? Second order is the right answer. Okay, this is the equation I want you guys to use. Right. If you have a reaction whose reactant decays by order 2, okay, if you have a reaction whose reactant decays by order 2, what happens if you double the reactant? Okay, how fast will the reaction go? Okay, it goes squared. If you triple the initial concentration of the reactant, how fast will the reactant go? It goes squared, which would be 9. If you quadruple the reaction concentration, how fast will the reaction go? 4 squared is 16. Okay, very good. Right, so that's what happens if that reactant is going to decay with order 2. You know we had this last problem, it decayed with order 1, right? That we did together. So you'll have either 0, 1, or 2. And these are the units for the half-life, okay, which is the time when 50% is gone. Right, the order, okay, the order is m minus 1 second minus 1. Okay, which is the same thing as 1 over molarity times seconds. Okay. That's the units of K. So the key here is to figure out what equation you need to use. How will you know what equation you need to use? Okay, you need to figure out whether the reactant is 0 decay, first decay, or second order decay. That will tell you what equation we need to use. All right, so bring this to the exam. Have this on by your side so that you can utilize these equations. Let's do some problems here in the last 10 minutes or so of class. Last 10 minutes of class. All right, the reaction 2A goes to B is first order with respect to A with a rate constant of 2.8 times 10 inverse seconds to the minus 1. 2.8 times 10 is 28. So 28 seconds to the minus 1, or you can say 28 over seconds. Okay, at 80 degrees, how long in seconds will it take for A to decrease? Okay, this is all about decay. How? Decrease from 0.88 to 0.14 molar. So what equations are we going to use? Okay, how will this decay? 2A goes to B. Okay, first order. So what equation would be for first order? Okay, first order, we'll utilize this equation. So natural log of A equals natural log of A naught minus KT. so what are we given here? It has a rate constant of 28 inverse seconds. And what is the initial concentration of A? .88 molar. What's the final concentration of A? Okay, so at some time t, it will go down to 0.14 molar. All right, so let's plug in these values here, and what are we asking for? How long? Okay, so we're asked in this equation how long. Okay, a time in seconds. All right, so natural log of A, which is 0.14. Okay, remember this is initial now. So natural log of 0.88. Okay, minus K, which is 28 over seconds. Okay, times T equals natural log of A at some time 0.14. Okay. So really want to figure out is how long will it take for this to go from 0.88 to 0.14. How long is that going to happen? How long will it take for that decay to occur? We use the first order equation because it tells us it's first order. All right, so let's isolate t here. So to do that, it's going to be the natural log of 0.14 minus the natural log of 0.88 equals minus 28 over seconds times t. So natural log of 0.14 minus natural log of 0.88. Let's do that on our calculator really quickly. Natural log of 0.14, okay, minus the natural log of 0.88, close parentheses, okay, minus 1.838. Is that what you guys are getting? Minus 28 over seconds t. All right, let's just cross multiply. Okay, let's cross multiply out. The seconds goes here, the minus 28 goes down there. So we have 1 minus 1.383 seconds. Okay, divided by minus 28. Okay, notice my units are in seconds. And then the minus cancels. And then I'm getting 0.0657 seconds. You can even multiply this by 1,000. So this is the right answer. You can multiply it by 1,000. 1, 2, 3 to get 65, 0.7 milliseconds. Okay, so this is how long. Oops, sorry about that. So this is how long it's going to take. Okay. So I did a cross multiplication to isolate t. The minus cancels, and this is what I got. This is the right answer. You can report this on your exam. If you want it in milliseconds, it's 65.7 milliseconds. So it takes 65.7 milliseconds for A to decay from 0.88 to 0.14. Okay, because, and you know, it's first order decay. All right, so yeah.
Why is it negative 28?
The equation has a minus sign here.
Oh, okay.
Minus k times t. So minus k, which is 28, times time t. Yeah. So here you just want to copy the equation from your sheet. Yeah, minus k, which is minus 28 inverse seconds, times time t minus, yep. And you notice that when you solve for t, this minus cancels. So t can never be negative. We don't have negative 20 seconds, negative. It's just positive. Time is always positive, okay? At least on this planet, okay? Here's the rate constant. 2.8 times 10 is 28. On the exam, I'll make it more clear. I got this from some old textbook, and I don't know what they wanted to do. Seems like they wanted to give students a hard time, but yeah. 2.8 times 10 inverse seconds is 28. But yeah, you'll get a more clear value for k, rate constant. All right, so those are some good questions. If you guys can stay, I will just hand out the exams.